quiz later? Someone's waiting until they come back. Oh, that one? Yeah, that one. There's a comment about the notation. There's one overall for both. All right, so we're still in 1.3, but I just said this is the second day, so I'll say 1.3b. We're still going to focus on evaluating limits analytically, but we're going to talk about this idea called the squeeze theorem. That will help us with the trig problems. So when we evaluate, our goal was to simplify, but a lot of the time with the trigs, we don't have a strategy for it. So we came up with this strategy to kind of help us with some of those trig expressions. So let's see. Let's start with a trig example first. And just something simple like this. So if you're asked to evaluate sine x, you still do direct substitution. All of that still works. And then you just plug it back into sine x on the unit circle at pi half. The y value is 1. So you get your answer that it is 1. Okay, but a lot of the time we are asked to evaluate things like this. So when we do direct substitution and plug in the x value, we get that issue. Let's see. So we get that sine of 0 is 0, and we get a 0 down here. And you guys call this, what do you guys call this when it's 0, 0? Okay, so we call it an indeterminate form, and when it's an indeterminate form, we have to simplify it. So since it's a trig expression, we don't have strategies to factor. We're not multiplying by the conjugate, things like that. So we came up with a theorem to kind of help us with these, and that theorem is called the squeeze theorem. So it looks something like this. It says there's a condition that is met. So they said if there's 3 functions, and the one we're interested in is the middle one. So there's 3 functions, and this condition is met where the g of x function is always going to be smaller than the f of x equation, but then the f of x is smaller than this one. Both of these are smaller than that one. Where it's actually close to x equals c. So we're not too concerned about whether this statement is true or it's far away, but what that means is a picture that looks like this. So let me draw you guys a picture. So c is some x value we are going to pick. And the equation that we are concerning ourselves with is this one, f of x. And the other two fits this condition. So right around close to C, G is going to be always smaller. So I'm going to draw G underneath. So there's G. And then close to C, the H function is always bigger. So I'm going to draw it above. So just maybe something above. So that keeps the condition true. It says that your graphs happen to look like this, where the f of x equation is squeezed between the other two functions. And the goal is to say something about the limit of f of x. So I'm going to give you the situation, and I bet you can finish the conclusion that something must always be true. Then, and I'll fill that in first. But so what they do is say it's hard to find the limit of f of x. Then the limit as we go to see for f of x is some value. And they said we can make this conclusion if we know something about h and g. So the goal is we want to pick something, an h or a g that we know. So say we know something about h. H happens to go to L at C, the limit. And then G also happens to go to L. So I'd say we're just guessing. What could you guess about the limit of f of x if both of those go to L? What does it go to? It goes to L. Because it's being squeezed in, and so this is what they mean by the squeeze theorem. But it only works at close to L, so or C, because if this condition doesn't have to be true, over here they could overlap. G could be greater than F or so, but right around here where we're interested in that region, we happen to know what those are. Okay, let's actually try an example first before we go back to the trig. One with just algebra to see if how these are used. So say here's the question. You guys are asked to evaluate the limit of some unknown function as we go to, where do I want to go to? As we go to 1, see if it works. Does it go to 1? Okay. So we want to figure out what the limit as we go to 1 for f of x, but I won't give you f of x. But say I know that this is true. I know that f of x is smaller than 5x minus 3. And f of x is smaller than this one here. Or bigger than that one. How the theorem gets used is since this first condition is met, f of x is in between, it is squeezed between these two. I just need to figure out what the limit of this one and this one is at 1. So I'll do a quick check. The limit as x goes to 1 of this one, what does that one go to? Oh wait, does this work out? What do I want? How about let's make this 4. Okay, so I plug in a 1 direct substitution into the smaller one. I put 1 in, I get 2 at the top. I put 1 in, I get 2 at the bottom, so they divide out to be 1. And then I check the one that's bigger as we go to 1. And that also gives me 1. So by the Screes theorem, what do you guys know about the limit as we approach 1 for f of x? What does it go to? 1. So it's forcing the function to go to that particular piece. Okay, that something comes to mind. So in our Desmo piece, there was this function here, and so this function is oscillating, but the Screes theorem works with this one because it actually is sort of squeezed between 2 functions, and it is squeezed between absolute value function, and it is also squeezed between maybe just the negative absolute value function. Oh, I'm not putting them in the right spot. So sort of like that idea where there's a function like this green one always larger than the middle one, and then there's the bottom one always smaller, and as we get closer to that, so what we do is then we would try to find the limit of the absolute value of x, and then the limit of the absolute value of negative x. If we know those limits, then we could just conclude something about this one. Does that sort of make sense? And then that brings something that reminds me that the homework problem didn't have any absolute value, so I forgot to tell you about what if we want to find the absolute value of the limits of those. That's why I had a note in there that don't forget to tell Mr. Zong to talk about absolute values. It kind of just appears later, and I always forget to go mention it. Okay, so that's the idea of the Screes theorem, but from the Screes theorem, they created 2 conclusions. So we'll rewrite it again. So right here, that is the Screes theorem, but the Screes theorem generates 2 conclusions, and it generates 2 special trigonometry limit. That we're going to use the conclusion to help us with trigonometry pieces. So the first conclusion is this one, only true if we're approaching 0, but it is that sine x over x, and they were able to pick 2 functions that squeeze the sine x over x, and right at 0, the top function and the bottom function happens to go to 1, so they said that right at 0, sine x over x goes to 1. Okay, so you can probably put a big box around that. The other one dealt with cosine. So they said right at 0, and we choose these because, I'm going to just use x instead of theta. They choose these because these were the conditions where it kind of caused the indeterminates. If I were a little bit left and right of 0, I would be fine because you will just get a number out. But if we were at 0, you get a 0 over 0 indeterminate. Same thing with this one. If you put a 0 in, you get 1 minus 1. Cosine of 0 is 1, and then you get a 0 down here. So it turns out that this function, they were able to find two other functions that squeeze this one as well and concluded that at 0, it goes to 0. Okay, so you just want to have those two in mind because they're going to help you. And it's kind of tricky because there's x's there, but you want to think about it like this. As long as this expression and that expression is the same, this theorem is true. So that's an example of the sign. And same thing with the cosine. We could have like a 3x here and a 3x there. We could still use this theorem. So I'd like to think about it as sine of something blank over something blank, as long as they're the same. So like if I had 2x, I need this to be 2x as well. Okay, so let's use this for that one that we got example 2 earlier. We were interested about the limit as we approach 0 for sine 3x over x. Okay, so this one doesn't look exactly like that theorem, but we can make it look like that theorem. What do we have to do with this function? We can make it look like this or this. It has a 3x there, so what do you guys want to see at the bottom? Yeah, you want to see a 3x there as well. So you're just going to multiply by 3x. But if I multiply the denominator, I also have to do what? Yeah, I have to multiply the numerator. So now you created something that is sine 3x. And if you're using properties, you can pull out this constant. What does all of this go to if I take its limit from our property? So this side goes to 1, and then that 3 gets carried. So yes, the final answer is 3. So those two conclusions help us with these here. Let's try another one. Okay, so sometimes we don't see, when we're dealing with trigs, we don't actually see sine or cosine. We might see the limit as x approaches tangent x over x. So I didn't give you guys any special trig limits for tangent. So the goal then would be to try to change tangent up to sine over cosine. So if you guys are working with this one, you're going to direct substitute, but when you do a direct substitution, it results into a 0 over 0 indeterminate form. So we have to simplify. And with trig, you just have to start to rewrite the expressions. So we'll start off with, say, rewriting it like this. Because tangent is sine over cosine. And the goal is to get this to look like one of those two special trig limits so that we can just use it to conclude. So another question that came up yesterday is, where does this x land? And that x will eventually land with this one. So you want to think about these problems like this. It's a fraction divided by x. And then you guys would say sine x cosine x times the reciprocal. That's why if you have this fraction divided by x, you will get it to look like this. So it lands in the denominator. Okay, so once you get it to look like this, you're going to use your properties of limits and just isolate the part that you want. You're going to put the x underneath the sign, and you know that since it's multiplication, you could actually do each one's limit separately. So separate. What is the limit of sine x over x as x goes to 0? 1 from our property, or 2 special limit. And in this one, if you guys plug 0 in, cosine of 0 is 1, 1 divided by 1 by direct substitution is still 1. So you get that your answer is 1, but you kind of want to show how we get to 1 for this one. Okay, let's try some other ones. You guys can maybe help me out with the steps. What do we need to start doing with these trig pieces to get the two special ones to appear if they're not there? Okay, so say I'm working with this one and secant x minus 1 over x appear. Now secant is 1 over cosine. So we had 1 over cosine earlier. If you did a direct substitution, you would get that cosine of 0 is 1. So the top is 0, and then the bottom is 0. So it is a indeterminate form. And since it's an indeterminate form, we have to simplify. So to simplify, I need to rewrite this one so that it changes to either sine x over x or 1 minus cosine x over x appears. Okay, so what's the strategy here? Maybe we will just start off with, you can just start off with maybe changing this to 1 over cosine. So trig identity. So I switch the secant to 1 over cosine. Okay, next step. Maybe get common denominators. So it looks like the denominator is cosine. So I'll times this second one by cosine over cosine. And then that's just going to give me 1 minus cosine over cosine. Where does the x at the bottom land? It's going to eventually land with this denominator. So I get to that step. Okay, so it's starting to look a lot like one of my special trig limits. So all I have to do is kind of isolate this one together. 1 minus cosine x over x, and then isolate the 1 over cosine again separately. And then you do each one's limit separately. And you should be done from there. So if you do this one's limit, you know that we have the special trig limit, and it results into a 0. And if you do this one's limit, you're actually okay to just do a direct substitution, because when you put 0 in, cosine of 0 is 1. 1 over 1 is 1. So you get, finally you get 0 times 1, and your answer ends up being 0 for this one. Okay, let's try one more, and then I'll kind of have you guys practice some of them, see if you could figure out what we're going to get to. Oh, maybe something small like this first. Okay, sometimes you guys get this piece here. Chances are, if we plug in 0, we're going to get 0 over 0. So it is going to be an indeterminate. How would you guys do this one? The special limits are already there. It's just that the x squared needs to be broken up into two x's. So rewrite this. Break up this x squared, attach it underneath that one, and then just break up the other one and leave it with this one here. Okay, so you broke up the x squared and the denominator into two. One land with the sign x, one land with this one. That actually now says that I have a special limit for this one, it is 1. And then I have a special limit for this one, it is 0. So my final answer ends up just being 0. Okay, so how about this one here? Let's do that. Okay, so this one actually should be finished fairly quickly because it already is the rule. All you have to do is take out the 1/5 in front. And then this has a special limit. It is 1. And you have your 1/5 in front. So you just get 1/5 that is left. Okay, maybe one more before we get going. And these only work if we go to 0. So you'll see that they're just going to 0. Okay, sine 5x, 2x at the bottom. I want to have something that looks like this piece here, so I can conclude it goes to 1. Since it already has the 5x, I have an x that appeared down there. What else needs to appear down there? That 5. So I'm just going to multiply by 5, multiply by 5. And then from there, we're going to take out this one and that one to the front, because they're constants, and our properties of limit say we can take out constants. And leave this one with this one here. Okay, this fits our special limit, and it's the trig through the squeeze theorem and the special limit, you would say that this ends up being 1. And then this just carries down. And you guys end up with 5/2. Okay, so we'll stop it there.